Chapter 6, Sampling and Sampling Distributions. We're going to cover the aims of sampling and basic principles of probability. Also cover the relationship between a sample and a population, which we introduced earlier in the course. We're going to go into more detail now. Identify and apply different kinds of sampling designs, and apply the concept of the sampling distribution. And finally, describe this important concept of the central limit theorem. So a reminder, a population is a group that includes everyone in a population. So that's everyone that we're interested in studying, whether it's individuals, objects, places, groups. And a sample is just a small subset from the population. In our notation, as we've been talking about the mean, we've used y bar. We've also been using lowercase p for proportion and s for standard deviation, s squared for variance, because variance is standard deviation squared. So that's notation when we have a subset of who we're studying. If we have all cases that we're interested in, we have the full population, the mean notation is different. We have this Greek letter pronounced mu, that's the mean. Pi, the symbol for pi is proportion. And then this is the symbol for standard deviation, lowercase sigma, and then squared for variance. So keep an eye on those as we cover differences between sample and population. If we only have a subset, we're going to use this notation. So a parameter versus a statistic. A parameter is a measure that we use to describe a population distribution. It could be the mean or the standard deviation, but only if we know all cases in our study. If we have a sample, a subset of people, we can still calculate mean and standard deviation, but we call that a statistic. We use a statistic to be a measure that we use to describe a sample distribution. Here's an example. Imagine that on the left here, we have a population. We have 1, 2, 3, 4, 5 rows and 1, 2, 3, 4, 5 columns. So these are 25 people. Imagine that this is the full population at an organization. And we then recorded race, ethnicity, and wanted to know a proportion, the proportion of white respondents. Well, from this figure, let's assume that 15 identify as white. Our proportion is pi. For the population, that's 15 out of 25, proportion is 0.6. If we didn't have the full population, but instead we just had a sample, let's say a subset of only 6 people, 4 of whom identified as white, we don't have a parameter, instead we have a statistic. The proportion of white respondents in this sample is 0.67. Lowercase p is 4 out of 6, 2/3 is 0.67. Notice that these two figures are similar. 0.6 is not too different from 0.67, but they are different. So how do we arrive at a sampling strategy that's going to get us something that is loyal to the full population? Let's talk about probability. Definition of probability, this is a measure that a particular event will occur. How probable is an event? Probability sampling is a method that we use in sampling. It enables us as researchers to specify for each case in a population the probability that it will be included in our sample. One way to ensure that our sample is indicative of what we would find in the general population is to use simple random sampling. And here, if we have a sample, we would design it in such a way to ensure that every member of the population has an equal chance of being chosen. And every combination of n number of members has an equal chance of being chosen. And the idea behind simple random sampling is you wouldn't want to end up with a sample that is limited to only a few corners of the population, we would want everyone across the spectrum of the population to have an equal chance of being represented. You would want the characteristics of your sample to match the characteristics of the population as much as possible. So now we need to reintroduce the idea of normal distribution in the previous chapter. In the graph below, notice that the standard deviation that's plotted here on the x-axis and the y-axis. On the y-axis, we see frequency of observations. On the x-axis is the distribution of observations with the mean right down the middle. And notice that that standard deviation across those two plots there changes the relative width of the distribution. In other words, the larger the standard deviation, the wider the curve. And here the wider curve, this green curve, B, is much broader at the base than the blue curve, A, which is clustered much more closely to the mean. So we want to pay attention to the mean of our sample and our populations, as well as the distribution. And you can calculate mean and standard deviation for either a population or a sample. Now, here's the dilemma. Ideally, of course, we would want the full population to have a precise measure of what's going on in the world. But realistically, in the real world, it's too expensive often to collect information about everyone. It's expensive, it's time consuming. So oftentimes we are limited to a sample. In fact, few, if any, samples really match exactly the actual population parameter that we're interested in. It's a great quote from the textbook noting, if sample estimates vary, and if most of the estimates result in some sort of sampling error, how much confidence can we place in the estimate? And on what basis can we infer from that sample to the population? Two very important questions that we'll come back to again and again. And we're going to learn some tools to help us answer these questions with real data. Now we're ready to talk about sampling distributions. We'll talk about sampling error and sampling distribution. A sampling error is the discrepancy or the difference between the estimate we get from a single sample drawn from a population and the real actual population parameter. So if we're taking a sample and that's giving us some idea of what the full population looks like, there might be a difference between the sample and the population, as we saw in the example earlier with the 25 observations and the subset of 6 observations, which was a sample. So there's going to be a discrepancy there. I want us to think about a theoretical distribution of every possible sample value we could observe for our statistics, like the mean or the standard deviation. You can imagine that the mean and the standard deviation that you observe in a given sample might change depending on who agrees to take part in your survey, which is a sample from the population. A little more here on sampling distributions of the mean. Now, if we think about a theoretical probability distribution of the sample, of sample means, for example, we can think of that distribution of sample means, so the central tendency measure across a bunch of samples. So that distribution would be obtained by drawing from the population all possible samples of the same size. There's another way of saying, what if we went back to the population and drew a lot of different samples of the same size? What would our mean or our average measure look like for a given outcome that we're interested in? If we go back again and again and redraw samples from that population, our means might be really similar, or there might be some discrepancies from one sample to the next, even if it's the same population. And related to this is this measure that we're going to call the standard error of the mean. Because we know that a sample is going to have some discrepancy, we want to have a sense of how much confidence we should have in our estimates and our statistics that we're going to calculate using data. And the standard error of the mean is a measure of the standard deviation of the sampling distribution of the mean. What does that mean? Well, it means that it describes how much dispersion there is in the sampling distribution of the mean. And because this is a formula, we can actually calculate the standard error of the mean. Standard error of the mean, SEM, is your standard deviation for a population divided by the square root of your sample size. So this assumes that we can observe the standard deviation of the whole population for all cases we're interested in. And then we're going to divide that by the square root of how many cases we have. And notice in this equation, because n here is in the denominator, right? The standard error of the mean is going to increase as the sample size decreases. The fewer cases we have, the higher our standard error of the mean. But if instead our total observations go up, we have more observations to work with, our standard error of the mean is going to decrease because we're going to lower the discrepancy, lower the standard error. And the standard error of the mean, finally, is always smaller than the standard deviation. Because again, we're dividing our standard deviation by square root of our observations. We'll come back to this in the next chapter and talk about why we're going to need this concept moving forward. The last topic we need to talk about is the central limit theorem here in chapter 6. So if all possible random samples of size n are drawn from a population with a mean of mu and a standard deviation here of sigma, then as n becomes larger, the sampling distribution of the sample means, the sampling distribution of the sample means becomes approximately normal, with a mean of mu sub y bar and a standard deviation of sigma divided by the square root of n. What does this mean? You may have heard of this as the law of large numbers. The more observations we have, the more we think the sampling distribution of our sample means is going to resemble a bell curve, an approximately normal distribution. The law of large numbers, and we're going to use this to work in our favor as we try to calculate how confident we are that the means we observe are, one, reliable and have a strong signal, and two, are stronger than the variation around that signal. We'll cover that in detail in the next chapter. For now, we should know that the central limit theorem is going to work in our favor. The more observations we have, the more that we can assume that the sampling distribution of the sample means is approximately normal. Revisiting our vocabulary, we started with population and sample, the difference between those two concepts, where parameter corresponds to the population, a statistic corresponds to the sample. Calculate parameters for a population, statistics from a sample. We also introduced ideas around probability and the sampling distribution. And we ended with the standard error of the mean and the central limit theorem. See you next time.